Hi, my name is Lucas Lopez-Jensen, and today I'll be helping you put trigonometry back together. So hopefully after the last video, you all have a grasp on the 6 basic trig ratios. If you're still having trouble finding sine, cosine, tangent, cosecant, secant, and cotangent, try rewatching the last video or finding more resources. If all of those make sense to you, we're ready to go. Today's video is about inverse trig ratios. Basically, we're taking the 6 ratios from before and undoing them. To understand what this means, think of the square function. You take any number, multiply it by itself, and there you have it. It's squared. This can also be seen as the number being raised to the power of 2. How do you undo this? You find the square root of the number. This is the value that, when multiplied by itself, becomes the given value. This can also be seen as the number being raised to the power of 1/2. In algebra, if you want to undo a square function, you use the square root function because we define the square root function to be whatever undoes the square function. The same principle applies to trig ratios. While trig ratios like sine use angles in their input and ratios of side lengths in their output, inverse trig ratios like arcsine do the opposite. They use ratios of side lengths in their input and angles in their output. We only really use 3 inverse trig ratios, and each of them corresponds to a trig ratio. The inverse of sine is arcsine, also written as sine to the negative 1 or inverse sine. The inverse of cosine is arccosine, also written as cosine to the negative 1 or inverse cosine. The inverse of tangent is arctangent, also written as tangent to the negative 1 or inverse tangent. Weirdly enough, each of these inverse ratios has 2 names, and they mean the same thing. The only reason I would ever use one over the other is teacher preference, but a college calculus teacher got me to prefer the arc names to the inverse names since their notations are a little clearer. So for this series, we'll be referring to them as arcsine, arccosine, and arctangent, but if you prefer inverse sine, inverse cosine, and inverse tangent, follow your heart. Now, let's see how these ratios work. Say that we have a 3, 4, 5 right triangle with this angle marked as theta. We know that the sine of theta is 3/5 since this is the opposite side divided by the hypotenuse. Using the inverse trig ratios, we can find the angle measurement of theta. Sine of theta is equal to 3/5, so theta would be equal to arcsine of 3/5. Remember how inverse operations undo their original ratios? Here we used arcsine to undo sine and find theta. Our answer, arcsine of 3/5, looks a little strange, and we'll have to plug it into a calculator to make sense of it. For this problem, you're going to want to make sure you're in degree mode and type second sine 3/5. You should get about 36.869 degrees as your answer. Now, you try one. How can you use inverse ratios to find the angle measure for theta? Pause the video now and try on your own. If you can't figure it out, I'll write a hint for you and eventually the answer. Go ahead and pause the video now. Alright, here's your hint. You'll have to use an inverse ratio that deals with the opposite and adjacent sides from theta. Got it? Rounding to 3 decimal points, you should have gotten that theta is 22.620 degrees. If you didn't get it, you should know that this is arctangent of 5/12 because tangent of theta is 5/12 and you need to reverse that. Now, shifting gears, remember how the inverse ratios use the outputs of the regular ratios as inputs and vice versa? That applies to all values of the ratios, not just angles and leg lengths. For example, as we covered last time, the cosine of a 30-degree angle, or of pi over 6 radians, is root 3 over 2. That means that the arccosine of root 3 over 2 is 30 if you're measuring in degrees, or pi over 6 if you're measuring in radians. Assuming that you're clear on how these inverse ratios work now, let's try something a little harder. Ready? Let's go. Using just this angle and 2 sides, solve for beta, alpha, and b. Pause the video, give it a try, and unpause for answers. Got an answer? Great! We only have beta's adjacent side and hypotenuse, and we only have alpha's opposite side and hypotenuse. This tells us which ratios to use for each angle. First, let's solve for beta using cosine. We know that cosine of beta is 4.5 over 7.5, so using the inverse ratio for cosine, we can conclude that beta is equal to arccosine of 4.5 over 7.5. And typing this into our calculator on degree mode, we know that beta is about 53.130 degrees. Now, you could use a property of triangles to solve for alpha without using inverse ratios. Since you know 2 of the 3 angles in the triangle and that their sum has to be 180 degrees, you could solve for alpha like this. 53.130 plus alpha plus 90 equals 180, so therefore alpha would be 36.87 degrees. But this method includes a rounding error, and you may be using a wrong answer for beta. So it's safest to solve for alpha using inverse ratios and sticking to information we know is true. We know that sine of alpha is equal to 4.5 over 7.5, so using the inverse ratio for sine, we can conclude that alpha is equal to arcsine of 4.5 over 7.5. And typing this into our calculator on degree mode, we know that alpha is about 36.870 degrees. When you're rounding to 3 decimal places, this answer looks exactly like our last one, but remember that the real measure of alpha is more like 36.86989 degrees, and you can only find that answer through this method, so this way is more exact. Now let's solve for b. While lots of you might use the Pythagorean theorem here, we can actually do it using trig ratios as well. This way will be a little less accurate since we're using complex angles, but it'll be good trig practice. It's generally safer to use the Pythagorean theorem here, though. There are lots of ratios we could use here, but for now, let's go with cosine of alpha. Since alpha is about 36.87 degrees, we know that this would be cosine of 36.87, or b over 7.5. Now we can use some algebra to isolate b by multiplying both sides by 7.5 to get 7.5 cosine of 36.87 is equal to b. Next, we run this through a calculator on degree mode to get an answer. I'll be using the exact value of alpha we solved for earlier using the answer button to get a more exact answer. The calculator tells us that b equals 6, and if you were to use the Pythagorean theorem, you would get the same answer, b equals 6. And now we know all the side lengths and angles of this triangle after starting with just 2 sides and 1 angle. I hope you all understand how we got here, and if you had trouble, try rewatching the video again or looking for additional resources. Next time, we'll be graphing all the ratios we've covered so far. This will really solidify the concept of inverse ratios, since sine's input will always be arcsine's output for the same angle, and so on. I've been Lucas, and I hope that now trigonometry is a little less broken.